Training neural networks is notoriously computationally expensive. Depending on your model, you can spend hours or even days waiting for your hardware to process the data and update the weights. But you don't always need more hardware to speed up that process. Often, selecting the correct optimization algorithm can drastically cut down your waiting period. This chart previews the training loss for 4 different PyTorch optimizers. Over just 10 epochs, we are going to run a side-by-side test to see exactly how they compare in the race to zero loss. By understanding the math driving these algorithms, you can take control of your model's convergence time. Here in our working environment, we have our initial PyTorch setup and Python imports ready to go. We'll be using the Linnet 5 model architecture for this test. This grid displays our testing ground, the Fashion MNIST dataset. It gives us a dense collection of 60,000 grayscale training images to work with. Looking closer at these examples, you can see the dataset's exact constraints. Each image has a single color channel, and every item belongs to one of 10 distinct classes, labeled 0 through 9. To keep our code clean and avoid repeating ourselves, we define standard helper functions for our training and validation loops. By locking in the model, the dataset, and the training loops, we isolate the optimizer. It is the only variable in this test. Step 1 is establishing our baseline. For that, we use standard stochastic gradient descent, or SGD. This is the core mathematical update rule for SGD. When we configure this in PyTorch, we map the math directly to the code, specifically the alpha variable, which translates to our learning rate parameter. Standard SGD is reliable, but it has a known flaw. If the terrain of your data is uneven, the algorithm easily gets stuck in local minima and shallow plateaus, halting your progress. The easiest way to fix this is by adding a technique called momentum. Instead of only looking at the current step, momentum carries forward a fraction of our past gradients. Mathematically, this modifies our standard update rule by introducing a new velocity term. In PyTorch, we implement this by routing the math's beta variable directly into the SGD class as our momentum parameter. By factoring in past steps, we give the algorithm the physical inertia it needs to roll right through those suboptimal plateaus. Both forms of SGD apply a single global learning rate to all parameters simultaneously. If some features in your data are sparse while others are frequent, a one-size-fits-all learning rate slows down convergence. RMSProp solves this by calculating adaptive learning rates. It scales the updates for each individual parameter based on a moving average of recent gradients. This code snippet shows the PyTorch initialization for RMSProp. Notice 2 unique configuration arguments, alpha and eps. The alpha parameter acts as a smoothing constant. It weights the moving average of the gradient, allowing the algorithm to continuously adjust its slope for specific parameters. Because the scaling involves division, the epsilon parameter is added to the denominator simply to prevent the math from returning a division by 0 error. RMSProp shifts the strategy away from raw forward inertia, relying instead on calculated, precise adjustments for every weight in the network. Momentum gives us physical inertia. RMSProp gives us adaptive scaling. Combining the 2 concepts gives us the most popular optimization strategy in deep learning today. That powerful combination is the Adam optimizer. These equations define Adam's update rule. It tracks both the first moment estimate, which acts like our momentum, and the second moment estimate, which scales our learning rate just like RMSProp. When we call this in PyTorch, we map these 2 mathematical concepts directly into the betas argument. The first value controls the momentum decay, and the second controls the adaptive scaling decay. Adam is the industry default today because it merges the best traits of both evolutionary steps into a single, highly stable function. Now that the configurations are perfectly set, we initiate the final training sequence for all 4 optimizers simultaneously to watch them run. On this training loss chart, the red line for standard SGD remains sluggish with high loss. Adding momentum, the blue line drops immediately. However, the adaptive algorithms dominate. RMSProp's black line and Adam's green line plummet within 2 epochs. The complex math happening under the hood translates into massive efficiency gains right at the start of training. Looking at the final epoch on this chart, the gap in training loss between the baseline SGD and the adaptive optimizers is massive. Adam and RMSProp effectively finish the job before SGD even gets halfway down. However, this validation loss graph shows a different angle. By Epoch 10, the final performance across all 4 methods actually looks quite similar when evaluating unseen data. It's important to remember that an optimizer's strict mandate is only to achieve fast, stable convergence on the training data itself. By choosing Adam or RMSProp, you spend significantly less time waiting for convergence to happen, which saves raw compute time and shortens your iteration cycles. For your next PyTorch project, set Adam as your default starting point. From there, you can start experimenting with learning rate schedulers to push your model's performance even further.